So this is our second optimal control theory Beluga course. Today we're going to cover installation of Beluga, um, in, and then Python tips and tricks. So the goal of this is to allow one to kind of dive into Beluga and the Python code. And to help with that, I'm going to kind of cover, looking into Python, what Python is, and helpful things to think about when using Python. Okay, so I'm going to start with kind of talking about Python super generally, and then we're going to go into installation things, and then I'm going to go through the Python tips. So Python is a very high-level language. This is actually, their website uses the word very in this, and it's interpreted as well. So what interpreted means is that unlike a compiled language, when you write Python code, it does not have to go, so a compiled language, you write the code, you run it through a compiler that turns your code into something, machine code that the machine could read. Python has an interpreter between your code and the hardware. So the way that works is you have your source code up here. This is the thing you write. This would be in a .py file. And then that goes into an interpreter. This is written for your machine. It'll compile for your machine. So this is machine specific. So it'd be different. The actual code that runs would be different if you have an ARM processor or an Intel processor, different systems and different operating systems as well. And then this interpreter talks to the hardware. And inside this interpreter, you actually have two steps. So it's you can picture this as a box. And within there, you actually have a compiler, which is it's compiled, but it isn't. This compiler compiles to what they call a Python virtual machine. And this is similar to what Java does. So this compiler can be really fast because it only has to compile to one type of hardware. So there could be a one-to-one correspondence of functions to compiled, and then what it compiles to is called bytecode. So there could be a one-to-one correspondence, and that bytecode only has to run on the Python virtual machine. And then that Python virtual machine communicates to your hardware. So some people think that Python being interpreted is why Python's slow. That's actually not true. The reason why Python's slow is the way that it's dynamically typed. So Python is dynamically typed. This is like MATLAB, but I'm not 100% sure on the MATLAB implementation. I think MATLAB is more strictly typed, so it doesn't have the same speed slowdowns. And cover that shortly. So and what dynamically typed means, so if you work in a language like C, right, you have to declare your variables. So you would have to say int a, and then you would have to declare it, and then you can later say a is equal to 5, right? But this is not, for a dynamically typed language, you don't have to do that. It does it on the fly. So then, and this is unique, and this is actually good to think about in Python, every variable refers to an object's address. So if you know languages like C is the one pointer because they use this most often, you have pointers. Yeah, in C you have something that's like a normal variable and then you have a pointer, and then a pointer is an address. In Python everything's like a pointer. Um, and that allows you to do quite interesting things. One of which is that um, multiple aliases can be ascribed to one object. Let me know if you have questions on this. So say we have some object in memory. I was going to draw it out, but here, if this is our memory, okay, and here we have like an object. And it has its little address. I don't know, I could draw a more complicated picture, but see, the object is in memory, and it has some address, and then that has some number associated with it. But in the Python, you can have like A point to this, B point to this, C point to this, and then that's the same object. So if you change this object, then A, B, and C will change as well because A, B, and C are just, these variables just point to the object. So sometimes that could trip people up, but things can be done in place. And I'll touch on that a little bit later, I think. And then this is why Python's slow, but really flexible, is that types aren't enforced directly. So if you don't say like, oh, this function can only take integers, this function can only take floats. Instead, duck typing is used, and this is the official term for it. And this comes from that saying, if it walks like a duck and quacks like a duck, it's a duck. So like I said, this makes Python flexible but slow. And the way this works out is, say I want to add two numbers together. Like say A plus B. What this refers to is actually it calls A, and then it calls a method on the A object, which is add, and then B. So as long as A has a method add, it's going to add the numbers together. It doesn't care if A is an integer, A is a float, A is anything. It's going to add the numbers together. Likewise, if we call length on like C, all this transforms down to it calls the method length on like and these are underscores, but it calls that on itself. So this makes it so if you want to say make adding multiplication, you could overwrite the addition function and make the add do whatever you want, and you don't have to worry about including, oh, I have to write a special add or a special function for this type of these types. Like if you want to make a function that does something to both floats and integers, as long as all the methods you use can be called on both floats and integers, Python will do it. And then the last piece that's like kind of general over what we're going to do today is that the coding style that you should use is called PEP8. So there's a lot of things in PEP8, and if you get a good IDE, it will tell you whether you follow PEP8 or not. But in general, the convention is that variable names are lowercase, and it's like this form with an underscore. Class names are Campbell case. So it's like this, right? And then we're going to use 4 spaces for a tab. Other things will work, but this is like what is standard. So if you look into most large code bases, this is what they use. So it's good to get into the habit of using that. So I think that's as much. I might write some more things down later, but for now I'm going to put these notes aside. And then open up. Okay. So we're going to go through installing. I'm assuming to install Python, just go to this link here, the Python's website, and install it. It's fairly easy. For Windows, they have an installer. For the other system, they have directions. I assume that most people can do that easily. What I'm going to quickly cover is setting up a virtual environment. So virtual environments are good practice to use, definitely if you're developing code, because Python really relies heavily on installing modules and using third-party modules. And if you don't encapsulate those, you can say one project you need one version of NumPy, and another project you need another version of NumPy. That's hard to manage if you don't use virtual environments. What a virtual environment does is it basically starts your Python installation from scratch, and then you can control for each particular project what packages you have and where they're located. So I'm going to use the kind of basic virtual environment thing. You can also use Anaconda to do this. There's several methods. I actually like the really basic vanilla built-in way, just because you don't have to worry about licensing, you don't have to worry about installing anything else. So that's what we're going to do. So if you see on the left, what I'm using here is Windows Terminal and PowerShell. If anyone wants me to help them set this up in this way, let me know, but we're not going to cover it. But it's just the command line with I have Git installed already and Python installed already. So I'm going to navigate to where I keep my virtual environments. I'm going to make a new one. So we just do Python, and then this actually calls a module within Python, which is the env, and we give it a name. So I'm just going to call this Beluga course. So what it's doing is it's making a folder in that virtual environment folder that contains its own Python interpreter and the basic kind of classes like PIP and setup tools and stuff. So if you list that out, we see at the top we have Beluga course, and that's the one I just made. And then if we go into that folder directory, then this is what's inside. We want to activate that this virtual environment. So in scripts, there's a batch file called activate. This is particular to Windows. It's slightly different for Linux, but pretty similar. So if we go into scripts and activate, I'm in it, and you can see in this shell, you can see that it indicates that we're in the Beluga course virtual environment. So now if I call Python, the Python that I call is actually the Python included in this directory. So if I go into executable here, that's when I'm in the virtual environment, it's calling this Python executable. So that's just keep in mind. And in this lib, that's what site packages is, all the packages you install. So once again, everything is contained in this one folder instead of being on your path or in your program data. So you can kind of control it. If you don't like it anymore, you can delete it and start new. Okay, and then so now moving on to installing packages. In my opinion, one of the greatest strengths of Python is package handling, both externally and then internally in the files. So unlike other programs where you kind of just have to download the file and link it up and put it close and reference somewhere, Python handles a lot of, if you get third-party packages, it will handle that more or less automatically once you install it. So to install a package, you just use the command pip install, and you give the package name, and then that will install it from the Python package directory, like PyP. You could look up what's there online if you just Google search that. So for this purpose, I'm going to install NumPy. So pip install, it collects it, and then it will install, and it will install into, because we're in this virtual environment now, because we activated it, pip install will install in this virtual environment, thus leaving our systems, Python, and any other virtual environments untouched. So we successfully install that, and then you can also install multiple things. So I could say NumPy in mat.lib. So you can install multiple things, and it also installs the dependencies. While that's going, not that it matters. If you ever get, and this won't happen in a virtual environment, but if you ever get like a permission error, try pmp install and then specify user, and then only install for your user, and you don't get the same permission problems because installing on a kind of system level package. And then also, and then we're going to use this later. If you want the folder to be, you can install from folders too. So say you had your own Python folder, which is going to be when we install Beluga, then you could install it so it's editable. So then if you change something in that folder, it will change across any package that imports that. Yeah, so, and surprisingly, okay, it's done now. Okay, so now we're going to install Beluga. So let me go out of this. Alright, went to the wrong place, but it doesn't matter. So let me just, here, it's a simple, we git clone it, and then we install it. So let me make a directory. And okay, so then we just do this git clone command. So you navigate to whatever folder you want the Beluga files to be in. Assuming that you're wanting to engage in Beluga development, put that in, yeah, this is what you're going to change when you're developing Beluga. So if I just copy that over here, it's going to pull Beluga down from GitHub, and then we navigate, we have to go one folder in, and this is what it looks like inside. And you can make sure you're in the right folder because there's the setup.py, and then we just run the pip, and we install this folder. We make it editable so we can change it the period means this folder, and this dev is an option. It gives you some extra packages. So it's installing the prerequisites for Beluga as well as Beluga itself. So that's going. So that's as far as installation. If you have any questions in the future, let me know. Now what I'm going to move to is, and I'll test that later, but this interface here, what I have here is Python. It's the IDE I prefer to use. You can install it from JetBrains. This JetBrains Python, spelled, this is spelled like this. And once again, if you need help with that, let me know. But it's what I'm going to use now. So I'm going to open up this. This is just a Python file. See now that it's empty. In Python, you can set, down here you can set your virtual environment. So let me add the virtual environment we just made. So if I go to, browse, this might be helpful if you, so I go to Beluga course, go to scripts, and when I show that Python being, I just click on the executable and press OK. And now that's the Python I'm using in this Python instance to run a file. So let me go to this file I already made. If I run it, I can right click. Oh, it's updating the skeleton. But basically, yeah, I could right click and it will give me an option to run. That's going. This is still installing too. Yes, Eli, but it's okay. You could catch up. I just went to Beluga installation, so it's just getting exciting now, I guess, if it ever is going to be exciting. Did it say one? I thought I apologize then. Okay, so revisiting this. I'll go back here for now. Sorry for being a lot older, but we could check that Beluga is installed if we open up Python. So this is the Python interpreter, and that if I just import it, and we'll cover what this kind of importing a little later, hopefully. But if I import it, it's going to import without error. That means that it's installed. So let me, then you could quit Python here. Okay. I apologize for I guess there was an error in the WebEx link I sent out. It meant to be for 12:30, but I guess it said 1. That is my bad. I was changing times, so I must have grabbed the wrong calendar invite. So I really apologize about that. Anyone joining could catch up later. Okay. So let me grab this to the side. So I'm just going to cover, hopefully this isn't too basic, but I'm assuming that everyone's coming from MATLAB and going into Python. So the first thing, so how do we print from console? So I'm just going to do the first program anyone writes. And in Python, this is super easy. You just print hello world, output print to the console. See, it says hello world here. I set the option in Python, so this gives us the same terminal kind of interface you saw in the command line. Math is done as expected. So if we have that, and we run it, and I guess I should do this down here. But yeah, we have, see, that's the answer to this question. Let me do this instead. Sorry. Okay, and then we can do things like, so everything is expected with math. So if we take this here, right? So plus, divide, multiply is as expected, except for exponentiation. In Python, exponentiation is done with 2 asterisks, which is different than, you would think that it'd be a caret, but see how this gives a different result. That's not super clear what it's doing, but what it's actually doing is a bitewise XOR. So if we take this instead, and if you have a note, I'm copying and pasting from notes. But if we take this with the 0B meaning binary, we get 12, which 12 is here in binary. So not that this is important for using Beluga, but what it basically does is uses exclusive OR for each of the bits. So if you're in the habit of using carets, you might come across that, so just be careful. More advanced functions could be imported from the math library. So we could import math and say we want to take the sine of 2 pi. We just reference, and it should be 0. This is practically 0. So the math library includes things like sines, the exponent function, cosine, square root, things like that. So now I'm going to cover types. So you have, so let me just pull this back here, so you can see both the notes. Can people see what I'm doing in this and see my cursor? I assume I'm taking silence as yes. So we could define integers, so something like this. So if we just say int 1 is equal to 10, that's an integer, okay? You could also cast. Likewise, you could define floats. And I could check type, I can type and see class int. Strings are specified as you would expect, and then you could cast numbers into strings. This is kind of the first unique thing with Python coming from MATLAB, is that you could concatenate strings with the addition. And this goes back to what I was saying about the duck typing, is that in Python, the addition function for strings means that you add the 2 strings together. So if I take this, so I did not copy correctly. So basically strings, I get out 1 string, that's the strings added together. There's also string formatting. So there's references that you probably want to look at to do this. Just Google search format string in Python, but you can do things like this, where, so say we didn't know what this value should be and this value should be, but we want to output it to the console. We can take this and we can put that format, and this specifies the first element displayed as an integer, and this is the second element displayed as a float with 4 decimal places. So if we copy and paste that, so that is string 4. But see, now, in this case, that new line, so this is a new line, if I just output it, it's going to display the new line. But if I print, and then if you're in the interactive thing, 1 underscore means the last thing I did. It's like answer in MATLAB. The new line will display it both on 2 different lines. Then we get to lists. Lists are mutable arrays in Python. You can just specify them with brackets. You would think that they act like matrices in MATLAB, but they're kind of more nuanced and more flexible, but don't have some of the mathematical operations you expect. So you could fill out a list. You could actually put different types in a list. So if I look at list 2 here, see, I have an integer, a float, and a string. Because everything in Python is just a pointer to an object, Python doesn't care if you mix those pointers up, because it just sees everything as an object and doesn't care what it actually is. So as long as you could just, as long as you can put anything in a list. Indexing is from 0, like most programming languages, but different than MATLAB. So if I just take, so you get, this would get the first element, this would get the 4th item, and in this one, if you use a negative sign, it goes from the end. So this is the second to last. So in this case, you get 7, 6. 6 is the second to last, so that's what it outputs here. You also get slicing. This is, I guess, similar to MATLAB as well. So you have a starting point, an ending point, and then if you add this third argument, it's the number of steps. So this will do from the index 3 to the end. This will go from the beginning to index -2. This will go from index 0 to 5, skipping every other one. So if I show that, see we get 0, 2, and 4, skipping 1, 3, and then it ends at 5. You could also, I didn't include it here, but if you want everything out of a list, you can do that. It's more useful when you have like NumPy arrays where you have multiple dimensions. Adding lists together doesn't add the numbers in the list, but it concatenates them together. So we have list 1 plus list 2. So we have list 1, which was the numbers from 0 to 7, and then list 2 was 10, this 10.794, and I'm a string. So adding together makes the list longer. You either have to write a custom function to add the numbers in a list, or use a NumPy array, which I hopefully will show later. Okay, so appending, you can append items to a list just by calling the method append. So, and that works in place. Oh, I actually have to do this thing. So see how new items append, and then you could pop that off with this pop command. So that will actually return an item, but then eliminate it from the list. Tuples are immutable immutable arrays, so you could generate a tuple, but you can't change it after you make it. So tuple 1 is that, but if I say I want to make the first element 2, tuple object does not support item assignment. So once you have a tuple, you can't change a tuple. Then we have dictionaries. This is pretty integral to Python. A dictionary has keys and values. So, and then the way you reference the keys is by the name. So, so if we just do this, we'll get that 1 value. But if we get 2, we get 2. But the order is not maintained. So that's something to be careful about. If you put items in a dictionary in an order, they won't stay in that order. And the last kind of type object I want to cover is none. None is, like it sounds like none. So if you just want to, if you say like A is none, it's the same as saying it doesn't really point to anything. That's more useful than it seems, because there will be when you're filling out classes or checking if something exists. So I can say, so I can check if something exists by saying, is it none? And if it isn't none, then it exists. If it is none, then it doesn't exist. So that's important there. So here, the conditionals. so this is where we get to the point, and stop me if you have any questions. I think the basics were pretty basic, so hopefully everyone understood that. But I could have missed something or explained something poorly too. So okay, no questions. So conditionals. Conditionals are of this form. So in Python, unlike most other languages, white space is important. So the way you know, so instead of having if and then end or curly brackets or whatever other things languages use, like MATLAB uses end at the end of structures, Python just uses tabs. So you can say that this, you could tell that this statement belongs to this if because of the tab. And then as you tab back out, you're back in this section. And so you have if, else if, which is this else if, and then else. So let me copy and paste this, and we should get the first one. Right? A is less than 5. If I go and make this 6 instead, right, we get A greater than 5, and then if I make this 5, we get 5, right, equal to 5. You have while loops, kind of similar construction. So it's just while, what if B is less than 10, I could print B. It's very straightforward. You also have continues and breaks. So continue will skip to, so if I'm here, continue will skip back up here. Break will break out of the while loop. So if I just copy and paste this down here and run it, we count from 0 to 9. So then we finish that, and then we count B, we decrease B, counting down. But look, we skip 7 because we say if B is equal to 7 continues, so it never gets to this B, print B, and then else if it's equal to 2. So we never actually get to the 0 because when it hits 2, we break and we finish it. So yeah, so that's very straightforward. We have for loops. So the way for loops are specified are for some item or variable in an iterable. So this can be any iterable. In this case, it's a list. So what this will do is it will print these items. And once again, types don't really matter. So we have, yeah, the first item, the second item, the third item. You could also have functions that output, and this is kind of beyond what I'm going to cover today, but you have also functions, and I'm kind of blanking out what they're called right now, but they have like internal yields in them, and they'll basically iterate through this function, what this function returns, which is a particular type of class. But regardless, if you just want to go from 0 to 12, you can use this range function. So for index in range 12, we're going to print this index. And as expected, we get 0 up to 11, but that's because we're 0 indexing. So we want 12 indices from 0 to, plus, so that's there. So that's useful. That's kind of your basic for loops. I forgot my example there, but it doesn't matter because I could type one up quickly. So you have this. This is super useful coming from MATLAB, is this enumerates. So if you want to go through a list, but also have the index of the items in the list, you can use enumerate. So what this returns, it actually, the way this works, and this is kind of getting more advanced. So see, where this enumerate function returns a series of tuples. So in Python, there's kind of, in a lot of places, back up here, the parentheses kind of implied. So you think of this as a tuple like we saw before. And when I was going through the types, so the first element of the tuple is going to be an index, and the second one is going to be the item. But you could leave out the parentheses, and then I would just printed those down here with the format command. And then you could use zip. So let me just, do I have to, so let me type it down here. I can say I should do 4 A comma B, and then I could use this zip command here. And what this does is if I have two iterables, then I can combine them together and find this really useful. So now let's just say 1, 2, 3, and then 2, 3, 4. Doesn't super matter. And then I'm going to print A plus B. So this is going to go through, and you get picture like a zipper, bring these together. So 1 would be paired with 2. So 1 would be the first given out to this A, and then 2 would be given out to this B, and then we're add them together. So if we put this down here, so we have 3, 5, 7. That matches what we expect. And then this is really cool that you can do in Python. It's called list comprehension. So if I want it, I could use a for loop inside of a list generation like this. So it might be a little, you just kind of read it like English, and then it makes more sense. So we have k squared for k in range 2 to 10. But this would generate a list such that that's the case. So if I do this, so see, we get what we expect. K squared, so 4, 9, 16, 25, 36, 49, 64, and 81. And like any of these other topics, I'm breezing through them so you know that they exist. So then in later courses when we look to Beluga, you could read it. So my goal is so you could start reading Python code, and that you know something exists, so when you're writing Python code, you know what to look up. There's also this cool thing for this here. You could do a list comprehension, but include a conditional. So this will only output if k is greater than 3. So in that case, yeah, we have the 16 like we expect, but it's only greater than 3. So for k is equal to 2, k is equal to 3, it's not outputted in this list. So we could filter values using this conditional. So that can make what would otherwise be long straps of code much smaller. Okay, so now let's move to functions. I'm actually going to do functions here from scratch. I'm going to do it in a file. I guess I didn't comment this, but when you write a file, when you put it into the interpreter, the file just more or less reads it into the interactive interpreter line by line. So you can do the same two things. So if you could write it in this interpreter down here, you can do it in a file and vice versa. So we're going to define a function. So it's called func, and then have it multiply two numbers together. So we use def, begins the function, and then we have the name, and then the arguments. And then we could, I don't know, make up some kind of equation. And then we could return the value. So this is kind of the, what we return. So then I can call it. Well, actually, let me run this here. So it runs, and then I can say, I can call this function to, and that's fairly straightforward. Let me get, I trust the math is correct. So this is in normal arguments. We could also do something like this. So arguments are inputted into a Python function as a tuple. So say I don't, so I can also do something like this with this asterisk unpacks this, and then I can say 1, 6, and I get 4. So I could either specify the tuple directly in the function as that, or I could unpack a tuple into the function argument, and then it will unpack here. That's helpful when you're doing more advanced things. Likewise, you can specify keywords. So say I want to do something, in this case I'm going to pull this function here. So if I want to do, in PEP8, specifies that you keep 2 spaces between functions. Say I want to do this. So I have my initial arguments, but then I could specify what are called keyword arguments. So in this case, I'm specifying what operation I want, and a default value add. So this is a way you could add default values to functions. So I can say, okay, so take an X and Y, and then this is optional. This keyword is actually optional. But if it's add, it's going to add the numbers, and if it's subtract, it's going to subtract. So it's actually going to be faster if I just copy paste that in there. Okay, so if I take 2, and then 1 and 2, see, I didn't specify the keyword, so it added them together. I can specify it as add, and it's going to add them together. I can do sub, and it's going to subtract them. Okay, and then, so like the first arguments, the normal arguments were specified as a keyword, or as a tuple. The keywords are specified as a dictionary. So you can do this double unpacked kind of double asterisk, and I can say keyword op is add. Just have to do it again. So that's a key, and then I do add, and then I unpack it. But you have to unpack it twice. And then C is 3, and I can change this to sub, and it'll be -1. So there's objects behind these functions, and so these are dictionaries, and this is a tuple. Okay, so that's functions. There's also another interesting thing about functions is you could embed functions in each other. So unlike MATLAB is much stricter with functions, but because functions 2 are just objects, so I can say function 3 and say I take X and Y, colons necessary. But then in here, I say I define another function. And then now take Z. So I can say return X plus Y plus Z, or times Z. Let's do that. And then I could actually return this function. Beluga does this kind of thing a lot, so that's kind of why I'm covering it, even though it might seem a little advanced. So if I don't call the function with the parentheses, but instead I just leave it with this name, it will treat the function as just an object. It actually has a method, and I can show you that after this. It has a method called call, and that's what you do when you use parentheses. I could actually inherit something too. I could say A is equal to 2, and I could say, so I included this as well, because this function is in this function scope. So when I generate it, it'll take whatever you can see, like on this line, you can use it in the function, but it gets frozen at the time you generate the function. So later on, if you change A, it's not going to change what's inside the function. So, okay, so let me take this. So I can say so I call that function, and if I look at this one where I just generated, it's a function here. And it's a function, so this is the size. You could call this, no, not that, sorry. Basically this has I'll show that later, but then I can call this with a z. So let's make a z1. So it's 14. So we have 3 plus, that's 7 times this 2 is 14 times 1, 14, and then we could do 2 and get 28. Just to show what's happening internally, this has this method call. So when you do this, or if you do this, it's the same thing. So anything that has this method call, you can call like a function. So if you really wanted to, you can say a is equal to 10. This is kind of getting aside the point, but I could say a is equal to 10. So a is an integer, but then I could say a call. This is kind of really abusing stuff. I can make that equal to this inner function here. Oh, I actually have to do it more complicated than that. I'll revisit this kind of thing later. Yeah, I have to initialize it and everything. So forget that I'll do that. Well, actually, so is there any question about functions? Okay, well, if there's not, I'll go to classes. So, yeah. After the fact, no. So, like, say, if I go here and say, like this, right? And I run this. So I redefine A after the fact, but this is still giving 28. If I had to do that, where I want to redefine A after the fact, I would use classes. And I can show, yeah, that's what we're going to move on to now. So yeah, I don't think I didn't generate anything here. So, I wasn't super creative. So I don't know, does anyone have an idea? What do we want this class to be? If not, it's going to be an animal. Okay, so I'm calling it an animal. So when you generate classes, so this is not actually necessary in this case, but I'm inheriting from the basic object. So you have a class, animal, and as I stated before, classes are in camel case capitalized. So if this had 2 words, I would say like, I would do it like that. That makes the code a lot easier to read because you know what's an instance, because since every variable is an instance of an object, even functions are instances of an object, everything that's an instance, so like a particular thing, is lowercase, and everything that is a class, so to describe multiple different objects, is uppercase. That's the method that's the thought behind the method. So I'm just going to use the pass keyword here, and what this is going to do is just make this function class, but it's empty, it doesn't do anything. But you can see it's class, it's in the namespace main, which hopefully I'll get to cover, and it's of type animal. If I want to generate it, so I can say, so that's just the class, and then you can make an instance of that by calling this class type. So like a pig is going to be this kind of animal. And then see how this is class animal, and this is animal object at some specific memory location. So this memory location is where the object sits. You're never going to actually have to know that, but every object you have has a different memory location. And then you could, getting back to what I was talking about, everything's an object. I can say, I'm not being creative, but see, if I go pork, see how these memory addresses are the same? So if I actually say this equal to 4, yep. Did you do this class animal inherit from object path thing first? So you type this line here, and then you typed this here. Yeah, because as of now, up here in the console, different things. I'm typing things up here so I don't have to edit them. Like, I can edit them, but right now I'm just kind of exploring and I don't want to save anything. So this is a file, and this is a console. Yeah, sorry if that was a bit not clear. Okay. So yeah, going back to what I was saying. So see, I added, and I'll cover that really briefly, but in more detail. But just to go back to the multiple aliases pointing to the same object, we have pork and we have pig. I said the attribute legs is equal to 4 on the pig. If I go pork and then pork.legs, it's had 4. So even though I didn't set this on pork points to the same object at the same memory location, so pork is going to change as well. So that's what I was talking about earlier in the kind of extreme dynamic type thing. And that you have to kind of get a hang of. So say we want this, so going back up here, say we want this class to be more interesting than just being an object, a generic object. We can, so when a class is initialized, it calls on itself. So there's actually a call which is more advanced called dunder. And when I say dunder, I mean this double underscore. So see how you double underscore front and back. That's like a special type of class special type of method in Python. So we have this dunder init. Let me pass this so I don't get this quickly on. So actually, this is kind of probably more advanced than I should cover right now. So you have these two. So when you say generate an object, so like this animal object, dunder new is called first, and then that kind of not initializes because init initializes, but dunder new creates the object. There's rare cases where you need this, but you're not going to need this now. So I'm going to ignore dunder new and focus on dunder init. Dunder init is the second thing that's called on an object. So when I make an instance of the class animal, dunder init's called, and it's called regardless. And this is where you contain the arguments. So say, in our case, say every animal has a name, right? So we can take in the argument's name like a function. You can include keyword arguments in here as well. So I can say, let's say it could either be a pet or not, and it defaults to not being a pet. So pet is equal to false. So then this self, so every method in a class takes in self. Not every non-static method. So based on how much object-oriented programming you had before, there's similar concepts in virtually all object-oriented programming languages. Self is the instance of the animal class itself. So to initialize this, we say self is equal to self.name is equal to name. So what we're doing is we're assigning the name, what we input as a name, to the attribute. So this defines an attribute. and then we're just making it equal. Then we can say self pet is equal to, actually let me change this to owner. That might be more interesting. And then I'm going to initialize it to none. So you default to not having an owner, but if you have an owner, then you can include that too. So this is a place where you can use that none keyword and none type. So when animal started, it's going to take these two in. And just to have something to do, and it's a little morbid. So let me put alive here, and let's say this always initializes as true. Here, because I need to have a method that does something. So let's have the method be die. I don't know. I didn't want to make it too complicated. That's the simplest thing an animal could do. Is just die. Wow, this is morbid to be on YouTube. So see how this automatically inputs self. So we could change. So we could reference this self object, which contains what's up here, and then if this is true, we can say self.alive is equal to false. So see how I can change attributes now. So let's take this class down here, and then so we have this class. I'm going to make it a 1 so people don't get upset when I kill it. I'm sorry, guys. So I could initialize this animal. I can give it a name. I'm calling it Wormy because I'm not that creative. And I'll make it my worm. I could say Sean, right? So we could access attributes of this worm by saying, we could say, what's its name? What's its owner? Okay. And then we could check if it's alive. It's alive. That's true. And then we can call the method on that, which is die. So it's going to. So see how I didn't do the parentheses. So this is actually an attribute as well, but it's a function attribute or method attribute. And it does this. So I call it. Now if I check if it's alive, it is not alive. So in Python, everything is public. So if you're at all familiar with other object-oriented languages, they make a distinction between public and private. Python doesn't. Python has like a soft workaround for public versus private, and then that's to put a single underscore. So say I don't want people looking into owner. I don't want them to know that this is my animal or whatever. I can put an underscore. This is more just like a warning and kind of like a note. Like you could still access this. So if I go, let me just run it actually this way. If I do the same thing, right? But now if I go 1, this door will actually show you what attributes it's a directory, shows what attributes it has. And that's actually the command that I missed earlier when I was trying to show something else. But this is all the things that an object has. And you can see back, it actually doesn't show up what's the single underscore here. But if I really wanted to, I can find it. I can just type it and it will come up. So this is as protected as you can be. It's a single underscore in Python. It's my understanding that private methods are going by the wayside anyway in other languages, so that's not that big of an issue. And then this is kind of like saying you don't need to look at this. And then we can also do static methods. So static methods are the same no matter for the class, no matter any of the attributes. So it kind of acts regardless of attributes. So let's just say sit. I guess different one can't really sit, but I'm not that creative, and I didn't get these examples worked out fast enough before this lesson. So this doesn't, and let's just say duration. It's not going to do anything. Or I could just actually, I'm going to use the Python wait command. I think that's the input time. So up here, so I know I'm importing the package time. And go time that, oh my god, time dot sleep. Let me just change this to sleep. So see how this is static because it doesn't need the self. It doesn't need to know what the attributes are. It just needs to know this duration. So this will be the same for any animal object. So yeah, it'll be the same for any animal object. So let me run that again, and then I can make my worm sleep for 2 seconds. We wait 2 seconds, and then we get the thing again. The sleep command just halts any kind of operation for the number of seconds you put in. So yeah, so we have, this covers attributes, private attributes, methods, and kind of static methods. And then, so the way, and the scope works the same as functions. So if I declare something in here, things later can see it. And if I declare something in this object, things within the object can see it. And if I declare something out here, this class could actually import it in like a function. And then this quick inheritance thing. So like I said before, this animal inherits from an object. I can make a class that's like dog, right? And then I could say animal. So this dog inherits from animal, and then we type in this, and take in a name and an owner. So you have to redefine this interface, but then see it's warning me. It's saying, oh, this is not calling the superclass. So, right, so this super says what's above it, so from what it inherits, and then you call. So the way this works is I'm calling animal, and then I'm calling init on animal and putting in these. So just for clarity, I'm going to say owner to go to owner to just remember that's a keyboard argument. Actually, so I think this should also be self, the automated Python thing. No, wait, never mind. I guess that's not, I'm sorry, that's not needed for super. So I could either do this, or I can do this. I can call directly from animal. Oh, no, I'm sorry. This has to be self is equal to, actually, let's just trust it. I don't do inheritance that much. I could show you it in Beluga, actually, where this is used a lot. I just don't remember off the top of my head. But then we could say, give another attribute here and say self.legs is equal to 4. Because dogs have 4 legs. And if I run this, so I can have Fido equals dog Fido, and I won't give it an owner. We can do Fido owner. Okay, yeah, so I was right. So this doesn't have an attribute owner because I never make it equal to self. So I have to say here, if self is equal to this. Or actually, more. Okay, now I'm just messing this up. So actually, to remember this, let me just go here. I'll show it when it's done in Beluga. So if I go to data classes, so here I inherit a lot. So I have a generic structure, and then I inherit from the generic structure. Also, it does call self. So I was right to think that. So if we go back to here, self should be the first argument here. Which makes sense. Like, that's the way it should be. Because, so see how this is ordered argument? So I'm just feeding this object into where this object is, and I'll add everything that this object has here. So let's, I don't know why it's giving me that. Probably a Python, it's probably a Python problem, actually. So yeah, it's not an owner, but it doesn't matter because you should have a live still. Oh wait, let's check if it has the underscore owner. Yeah, okay, so it does have owner, and then it has a live, and then it'll actually also have the sleep, and I won't kill Fido, so we do the sleep, and you stay alive. Okay. Sorry for that. Actually, now we're going to namespaces and modules, and this I am set up for, and I'll speed up because we have 10 minutes left. So I've already kind of hinted at this, but you could import modules on the what's like the Python source path. So that's where you have Python installed, and then anything that's like in the current directory. So math is installed. Math is actually a default package, so that's installed here. And then we could take pi out and divide it by 8. Likewise, we could import things specifically, but then put them into the general namespace. So if we do from math, import the exponent and the log, we could take this. Okay? So let me run this so I have it available. So we can check. Okay, this should be 100, and it's 100. We can also import everything from a package. So this asterisk imports everything. That's useful to do if you're writing code just by yourself or just doing something in the interpreter. But if you're writing production code, you probably don't want to be using this asterisk because it muddies up your namespace, which is everything available to you typing. So you don't necessarily want the entire math package. So I suggest doing one of these two. So either here or this. If you do it this way, you have to use the period to reference things. And then you can also alias things you import. So here from CMath, which is what you need to do complex math, I input the square root by importing it as an imaginary square root. So check, and then that's a complex number, negative, well, I, which Python calls J. And as a side note, you could do complex numbers like this. So if you put a number with a J, that's like the imaginary version of it. So it's like that. We could also import things from the same directory. So this for classes file, which is where I have the animal, I could import animal. So then I could check, right? And this is the class we made. But see how before, if I go here, yes, let's go. If I reference it, this is Dunder main. That's the namespace you start with. So if you just run a Python file, it'll be Dunder main. But if you import something, see, the namespace is actually underscore for classes, and then the class is animal. So that goes to, that's called a namespace. And then we could make modules within that reference. So we could say from this example module input these values. Now I'll show you how that works. You define example modules kind of like classes. So you have this folder called example modules. In this Dunder init file, I have importing from this folder, but then I also have this example value, and then here I have more classes and stuff too. So this, when you import this module, you get the Dunder init is run like Dunder init run when you make a class. So there's a similarity between classes and modules in that way, and they reference them the same way. So they're kind of the same. There's a little nuance between. But that's good to look out for. And then here, so remember I said that if you just run a Python file, it is called, the namespace is Dunder main. Well, you could see what the namespace is if you go Dunder name. That says, okay, what's my namespace? Here it's main, but if I'm in a file, so say here, print name. And I'm almost done because the NumPy, SciPy, Matplotlib, I will just quickly walk through, and because I don't have much I can say on those, because it can take probably a month to talk about those in depth. So right, I said I could import this module function, so I have it here, right? So here I printed the namespace. So see how the namespace here is main, but the namespace here is example module, and then here's that from this example module here. And then here it's example module subfolder, which is this folder, and then this here. So that's its namespace, and then the namespace my interpreter is in is main. That allows, knowing those two things allows you to, if you have a library that you want to import stuff, but then you also want to test it or run things only if you run a file specifically, you can use this construction, which is actually fairly common, which is if name is equal to main. So like this Steve class is only going to be made if I run this file directly. So I can run this file directly, and then I have a Steve. But it's not run if I import it. So this is how you keep things that you don't want imported into other things separate, is just put this conditional, because as you import, basically what happens is the file is run from top to bottom. And yeah, that's all that import does. So once it hits here, when it's importing, it's going to say that the namespace isn't main, and then it'll stop, and it won't do anything more. So you'll see this construction a lot of places. And if you ever do multiprocessing in Python, this is actually required in a lot of cases. Okay, in the remaining 4 minutes is that NumPy will give you the arrays like MATLAB arrays. And you could check this. This website is actually a good resource because it'll tell you differences between things that you could do in MATLAB and things you could do with NumPy. So let me just run this super quickly. Okay, I had a plot, and that actually comes later. So if I look at this array, NumPy arrays are strictly type 2. So you kind of move out of the Python. NumPy is as standard of a library as you can without being actually included in Python, basically. But you have to install it. Everyone uses NumPy, but it gives you kind of like the math-heavy stuff that you want to get out of list. So I could add two arrays together. So I can say array, and I can have multi-dimensional ones. I can say array 1 plus 3, and this will actually work. So you add 3 to each. I can multiply each value. I can multiply them, etc. Okay, and then there's also SciPy, and then you can have like linspace as well, which is like linspace in MATLAB. So there's a lot of the same functionality. SciPy kind of fills out that functionality with adding more complex things like numerical algorithms. So this example here, these lines actually solve a ODE. So if you want to propagate equations like ODE 45, this is the Python equivalent. So I import solve by VP, which is the initial value problem from SciPy integrate. I have my ODE function, and then I can solve it, and I get a solution out with a time step in this. And then matplotlib is what is used for plotting by most people. And then that plot here, so this is our solution from SciPy. It's taking big time steps, so it should be sinusoidal, but it's taking pretty big time steps. So this is the solution, and then this is like a plotting script. And that probably not as clearly as I wanted to, but that covers everything I wanted to cover today. Is there any questions? So I will post the first one's posted on YouTube. They will be posted in a playlist on YouTube. I just got the link right before this meeting, so I'll send that out after this meeting and send out the link to the GitHub with the files for whatever files, the codes and notes and everything will be on a GitHub page. So I'll send that information out. Yeah. Yeah, so actually, so I could demonstrate, and you guys feel free to leave if you have something at 2, but I don't think I have a meeting at 2, so I'm going to stay on. I could stay on and answer questions. So say in this dog, I want to overwrite die. I can say like this die, and let me just say alive is, well, like, oh, okay. Well, I was just going to put went to heaven, but, so say I do this, it will, and I'm going to join files. So I run this. So I say title equals repeat start title, and then I say title die. He went to heaven. See, I overwrote this alive, but because this is just a object, so say I want to, from here, without changing this class, say in situ, I don't want die to do that anymore. I want die to be, I actually meant to cover this. You can do what's like a lambda, but I'm not, I don't want to do that now, but I'll maybe show that. That is, exactly, it's like that. So MATLAB has that kind of at thing that you can do. This is similar, so you can say like lambda, I don't know. It's going to be weird. It's not going to be consistent with die, but it could say lambda x, and then you can do x, y equal to x. So I can make die equal to that now. And then I can say 1 and 2, and then I get 3. And then I could actually change this because everything's an object, right? I could say die is equal to false, like say die, and then I say Fido.die, boom, you can't call it anymore. It'll be false. So you can just, so that's kind of what I meant, that methods are just attributes. And functions are just, so like I could add this, a call to this. So like say I call the animal object and then I say X, getting away from the animal thing, but I'll just print X. So let me rerun this. So I can make Fido again, and then I can say Fido. See it print. So I can now call Fido like a function too, because a function is just an object that has a call method. So I can call that object now. And yep. Oh, thank you. Oh, you're welcome. Thank you.